Hi, today we are going to talk about duration and convexity. To begin with, let's recap what we already know. Let me start off by drawing the graph that shows the price versus the yield to maturity of a bond. Let me denote the yield to maturity by R and the price of bond by P. As we know, there's an inverse relationship between P and yield, price and yield. So the graph of a bond price versus the yield to maturity looks something like that. Let's say we buy a bond at R. Okay, at R. Let's say we call it at R0 at the price of P0. Okay, R0 and P0. So the question we want to ask ourselves is, what happens when there's a rise in yield? Okay, so when the yield, let's say assume that yield moves to here, R1. From the graph, it's clear that we will experience a loss. The loss will be something like that. Okay, the price will drop to P1. So this is a loss that we experience when the yield increase to R1. On the other hand, let's assume that the yield falls to R2, and again it's clear from the graph that we experience a rise in the price, and the price will say becomes P2. Okay, so we make a gain on the profit of P2. So as we can see from the graph, when yields fall, we make a gain. When yields rise, we make a loss. So we want to express a relationship between the change in price versus the change in yield. So that straight away when we buy a bond, we know that okay, this bond, what is the risk of this bond when there's a rise or fall in the yields, and that is where the concept of duration and convexity comes in. Okay, so let me start again by writing down the bond price formula. Bond price can be represented by discounting all the cash flows of the coupons and the maturity par value to the present. Okay, so it will be C plus 1 plus R squared plus and so on plus C 1 plus R to the power of n here. And then let's say the final par value is m 1 plus R to the power of n. And we can shorten this whole equation into a summation format. Okay, summation, let's call this T equal to 1 C over 1 plus R to the power of T plus m over 1 plus R to the power of n. Okay, so basically this is straightforward, and it's just a recap of what we already know. We're just discounting all these cash flows into the present to obtain the price. Okay, to go into duration and convexity, we need to know this concept called a Taylor expansion. You can go and Google, but basically I'm not going to prove the Taylor's expansion now, but basically what Taylor expansion says that assume that you are given a function f. Okay, we can approximate this function is actually equivalent to assume that we assume this is a function. Okay, this is a function. We can approximate this function by an expansion of this function at any point. Let's assume that we are at R0. Okay, we can approximate this function at R0 by expanding this function into as follows. The value is R0, okay, plus first derivative is at R0 multiplied by R minus R0 plus half factorial multiplied by the second derivative as at R0 into r minus r0 squared, okay, plus, and so on. So there are a lot of higher order terms. I think for now we ignore the higher order terms. Okay, let's rewrite this equation by as follows: f r minus f r0 equals to r0 r minus r0, okay, plus 1 over 2 factorial is 1 over 2, okay, okay. So I'll ignore the higher order terms because they are negligible when r becomes very small. Okay, so given this equation, let's remember that f refers to this function, which is the function that obtains the price given the u. Okay, so if you look at this function, this equation, you can see that this one, right, is basically a change in price. Let's call this dp. Okay, so this one is basically a first derivative of change in price with respect to change in u. Okay, so this one is basically change in u, and so on. So this one is second derivative of price with respect to the u. Okay, again, this is the change in u. So when we rewrite this equation like that, this whole function becomes okay, I'll try to squeeze here. Okay, so this whole function becomes dp equals to dp over dr into dr plus half d squared p over dr squared into dr squared. Okay, so it becomes a familiar function when we divide this whole thing by p. Okay, so let's have 1 over p here and say 1 over p here. So we can from this formula we can see that when there's the percentage change in price is equivalent to this whole thing, this function plus this function. Okay, and we call these two functions the duration and convexity respectively. So we call this little thing here the modified duration. Okay, and we call this thing here the convexity. Okay, so let's relate these two equations to the graph. You can see that there's this dp over dr here, which is basically the gradient of the point which you are interested in. So let's go back to here. Let's assume that we are interested in R0. We bought the bond at R0. The gradient is given as such. Okay, so we are saying that the change in price is equivalent to the gradient divided by p multiplied by the change in the interest rates. So this is the change in interest rate if it moves to R1. Okay, and we are expecting the change in the price from P0 to P1 to be approximately equal to the gradient multiplied by the change in R, which will bring us to this point. Okay, we draw R1 to this tangent here will bring us to this point. Let's denote this as P1 prime. Okay. Similarly for here, right? When the yield goes down to R2, and if we apply this formula here, you see that the approximate price that this equation gives us will be somewhere around here. Let's call this P2 prime. Okay. So even though this expression here really gives approximate price change when there's a change in yield, it doesn't really give us the exact change because of the way the gradient is formed. It's a tangent to the curve. So the expression is not exact, and it gives a good approximation, but it's not exact. And and we can see here when the yield increase, it gives a larger than expected change in the price. The real change is at P1, and using just the duration alone, we obtain P1 prime, which is smaller than P1. And conversely, when there's a drop in the yield, the calculated price is P2 prime, which is actually less than P2, the actual change, because of the shape of the price yield curve, which is a bit of a convex. Okay, that's why convexity comes in, and we have to take into account the convexity in order to arrive at the vector approximation of the change in the price as a result of the change in the yield. Okay, so this one in short is the rationale and the proof of the duration and the convexity formula. Next, let me go a bit deeper into duration formula. Let's look at the dP over dr. Okay, now I've started a new sheet. Let me rewrite the bond formula. P is equal to C over 1 plus R plus C over 1 plus R squared, okay, plus so on. C over 1 plus R to the power of N plus M over 1 plus R to the power of N. Okay, so just write this one in shorter notation. P equal 1 N plus M over 1 plus R to the power of N. Okay, so this is a formula for one price. I want to differentiate this one with respect to R, okay, because let's look at the convexity formula. The modified duration. We have this dP over dr. I want to write this notation using an expression. Okay, so let me differentiate dP over dr. Okay, we can differentiate this one term by term. So this one will be minus 1 C over 1 plus R squared plus minus 2 C over 1 plus R cubed, and so on, minus N C over 1 plus R to the power of N plus 1, okay, plus minus N M over 1 plus R to the power of N plus 1. Okay, so this is, you can see that this is actually very similar to this expression. Let me bring the 1 plus R term out. Minus 1 over 1 plus R into C over 1 plus R plus 2C over 1 plus R squared plus over 1 plus R N plus NM over 1 plus R power of N. Okay, so we can see that this expression becomes even closer to this one. Okay, so let me reduce it further. Summation TC over 1 plus R T and T equal to 1 plus NM over 1 plus R N. Okay, so let's take a minute to compare the derivation formula previously, which is, where is it? Okay, this one, 1 over P dP over dr. Okay, against this one. So let me write down the derivation formula. The modified derivation is given by 1 over P times dP over dr. Okay, so we have dP over dr here. Let's multiply by 1 over P here. Okay, divide this whole thing by P. So this is basically the modified derivation formula, and just one thing to note that because of the slope of the curve and the inverse relationship between the price and yield, the slope of the gradient is negative. So usually we put negative here to denote the inverse relationship between price and yield. So it's minus here and minus here. Okay. So just take a look at this formula. It's interesting because basically we are saying that for every of the cash flow we multiply by time. So assume that we have cash flow here, 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 and then this is N. Okay, 1, 2, 3. So we have C here, and then C plus M here. Okay, so basically we are saying that for each of these cash flow that we receive at time 1, we multiply by time. Receive at time 2, multiply by 2, and so on. So in a way, we can see that the duration is basically a weighted cash flow based on time. So as you can imagine, that's why a lot of people and a lot of traders regard duration as a concept whereby the longer duration you are expected to receive the cash flow further back in time. The shorter the duration you'll be receiving cash flows nearer to now, because of this weighting in the numerator of this summation. Okay, so if you imagine that assuming that this is before that, I want to introduce the concept of modified derivation, which is very simple, and it's simply the Macaulay derivation is simply 1 plus R multiplied by the modified derivation. Okay, so it basically simply remove away this term. This term disappears, and this will become the Macaulay derivation, which is a more commonly used expression as compared to modified derivation. Why? You can see that if this were a zero coupon bond whereby no coupon will be paid, and you'll be expecting you bought the bond at a discount and you'll be expecting to receive par in the future. So actually, if you use the Macaulay derivation and for zero coupon bond, this whole term disappears. Okay, this whole term disappears because C is 0. Okay, so you're left with this term. And if you look at this term closely, N, M, divide by 1 plus r to the power of n. Okay, this m over 1 plus r is basically referring to the price. Okay, this will be the price of the bond, and this price will cancel out the denominator price, which will leave you with n, which is the number of years of the bond before it matures. So for a zero coupon bond, this Macaulay duration is basically the number of years before it matures, and that's why the Macaulay duration is very useful. It's simply removing the denominator 1 plus r away from the bonified duration. Okay, I think that's all I have for today. There's actually a closed form solution for both the duration and the convexity. It's quite tedious to prove, and I think for now I won't be going through that. If there's anybody interested, just let me know. I'll show you the proof. Okay, that's all for now. Thank you.